Hello everyone, welcome to this short session on BJT Common Collector Configuration. So in a BJT Common Collector configuration, the collector terminal is common between the input and output side. Here the input is applied between the base and the collector, and output is taken from the collector and emitter terminals. Alright. So for the DC signals, especially for the DC signals, we have connected the configuration in such a fashion that base emitter junction is forward bias and base collector junction is reverse bias, all right, in the active region of operation. And we have connected the resistors over here to limit the current IB and IE. Yeah, RE is also very important in case of DC signal. So here in the input side we have IB, VCB. At the output side we have IE and VCE. So input characteristics is between VCB and IB, and output characteristics is between VCE and IE. Okay, and for the AC signal, the collector terminal becomes common. Okay, and input is being applied between the base and the emitter, and output is taken from the emitter and the ground, which is the collector terminal. All right. So this is for the AC signal and this is for the DC signal. When you study the advanced course on BJT, you will be understanding it why it is being done so. Okay, so for AC signal we don't consider the DC values and we only consider the time varying quantities. All right, so that's the reason why it is being connected like this. Okay, all right. Whereas DC signal, it's only used for biasing the BJT in the proper active region. Okay, so with this said and done, let us try to understand the input characteristics. So input characteristics is between VCB and IB as explained over here. VCB is the input voltage, IB is the input current, and IVCE is the constant output parameter. All right. So this is the graph of VCB versus IB. For two different graphs we get for two different values of VCE, where VCE2 is greater than VCE1, and as you can see for the same value of IB, the curve is shifting towards the for VCE2, uh, the curve is shifting towards the right hand side. So this is my input characteristics of NP and BJT in the common collector configuration. Okay, and this is the structural view of it, where we bias it in such a manner that it's in the behaving in the active region. So now let us try to understand from this characteristics as why by increasing the value of VCB, your IB is reducing. Okay, as you increase the value of VCB, IB is reducing, right? So we'll try to answer this question why. Okay, so VCE is given by VCB plus VB. We have discussed this equation origin. Here we are considering VBE constant, let's say. So for a constant value of VB means constant value, let's say we consider this IB value to be constant, and that value constant will be only when VB is constant. So let's say VB is constant. So as we increase the value of VCE, VCB increases. So as your voltage VCB increases, your width of your depletion base collector depletion region increases. We have discussed this in the last time that as you increase the value of VCB, your base collector depletion region increases and the effective width of the base reduces. Okay. So as the effective base width reduces, the probability of recombination of electron hole pair in the base reduces. So therefore the contribution of base current reduces, that is base current reduces over here. So as we increase the value of VCB, so that answers the question that why by increasing VCB your IB is reducing. Now the next question is for a fixed value of VCB, what happens? Okay, so let's say that VCB is fixed. Now as we increase the value of VCE, your VB also increasing. So that means what? Your more electrons are pushed towards the base region by the emitter. Okay, so more electrons are pushed towards the base region, right? So that means your IB value increases. So that's why over here for a fixed value of VCB, if you consider it for a fixed value of VCB, this one, your IB value increases. Okay, so let's say this is the fixed value. Yeah, this is, we consider with this fixed value of VCB, your IB increases. Okay, when your VCE increasing. So that is the reason why it is happening. Let me just get rid of this. Okay, all right. So for a fixed value of VCB, your when you increase the value of VCE, your IB also increases. Now here output current is IE, emitter current, and input current is IB. So IE upon IB is related to gamma. It is again a current gain in the common collector configuration. All right. Now the output characteristics of common collector, it's similar to your common emitter configuration, so no need to explain that. You all can refer that video. Here only difference is that instead of y-axis being IC, it's equal IE over here. So it doesn't matter, it remains almost the same, as the collector current and the emitter current are very close to each other. So the entire explanation will be valid over here. For you can refer the video of common emitter configuration. Okay, so you get three regions of operation: cutoff, saturation, and active region. So there the characteristics and the behavior is same. Now, let us derive the relation between this gamma and alpha and beta. So, IE is terminal current is IC plus IB, and gamma is basically IE upon IB, and IC is beta times IB, right? So, gamma can be written as IC plus IB upon IB, because IE is IC plus IB. So we can take this common. So IC upon IB plus 1, when IC upon IB is beta. So clearly we can say that gamma is 1 plus beta. Also gamma can be written as alpha upon 1 minus alpha plus 1, which is again beta plus 1, which is coming out to be 1 upon 1 minus alpha. So gamma is related to beta as 1 plus beta, and it's equal to, gamma is equal to 1 upon 1 minus alpha. Okay, so this is a relation between the three current gains in the three configurations. Now, what are the properties of common collector configuration? So it provides you a very high input resistance. As you can see, if you determine the input resistance from here, its value will be pretty high. Over here we can determine its slope and determine the input resistance. Its output resistance value will be quite low output resistance over here. From it, if we calculate the output resistance, its value will be quite low, and it has a very high current gain, which is 1 plus beta times. It has as you can see, the gamma is 1 plus beta, right? So the current gain is pretty high, and it has a low voltage gain. Voltage gain in fact is almost less than 1 or almost equal to 1, and it has similarly low power gain. So since its voltage gain is almost equal to 1, it's not used as a voltage amplifier. It can be used as a current amplifier, or it can be used as a voltage buffer. Okay, so these are some of the properties of common collector configuration, uh, for BJT. Okay, so that's it for this session. Thank you.